guys, welcome to our YouTube channel. Today we're going to be looking at Cameroon National Medical Entrance Examination, Faculty of Health Sciences, Buea, Physics 2021 Part 1.
Two electrical charges of -6 and +6 microcoulombs are placed respectively in two bridges A and B, 1 meter apart. The electric field is 0 at the point. Okay, so we have a diagrammatic representation of what's happening, and we can just come over here and then investigate throughout this line segment. Where is it that the resultant force on a unit positive charge will be 0? So let's consider the line segment between A and B first. So we're putting a unit positive charge here, and of course, since A is negatively charged, so A will be attracting this unit positive charge here. So the force A exerts on our charge would be towards the left of our charge, like that. And the force that B exerts on our charge would, again, because B is repelling, because B is positive and our test charge is positive, so B will be repelling our test charge. Let me just wipe that off. That is messed up. So B would be repelling it like this. Okay, it's still messed up, but I'm going to keep this one. So you notice that the two forces acting on our test charge are both of course towards the left. So we cannot, it's not possible for us to get a resultant force along the line segment joining A and B on this charge to be 0. All right, so the net electric field on this between A and B cannot be 0. Okay, so we're now going to go outside of the line segment AB, and we're now going to place our test charge somewhere around here, right, X meters away from A. So let's call that test charge M, and let's calculate. Let's investigate the direction of the forces that are acting on our test charge. So A, remember, that is negatively charged and our test charge is positive, so it's going to be attracting. So A exerts a force like this, it's attracting, right? And then B, remember that B is positively charged, so B will be repelling our test charge. So we'll come over here, the force B exerts on our test charge is to the left of our test charge. So you notice that these two forces are opposite in direction, so clearly it's possible to have a resultant force to be 0 here. All right, they are opposite in directions. The moment when their magnitudes become equal, boom, you get a resultant force on this charge to be 0, and hence the electric field there will be 0. Now the problem here is these two charges, the magnitude of the charges on these bodies are equal, and the Coulomb's force, right, the Coulomb's force of electrostatic attraction or repulsion is a function of the product of the magnitude of the charges that the two bodies have divided by the square of the mean distance between them. Now you notice that the product of the charges between any two pair, like our test charge and A and our test charge and B, the product of the magnitude of their charges would be the same, but the distance between them is not. So between M and A, the distance is X. Between M and B, the distance is X plus 1 meter. So you notice that though these forces are opposite in direction, there's no point along this line segment, even outside of AB, where we're actually going to get these two electrostatic forces of attraction and repulsion being equal to each other because of this difference in distances. So it's not possible. So you look through this answer, I say located outside AB at 1 meter, that's not true. Located outside segment AB at 1, that's not true. Outside the line AB. Okay, so this guy is a bit ambiguous. Now, outside the line AB, it's possible to have the resultant, the net electric field, to be 0, but you have to go at infinity where, of course, the electrostatic field due to either A or B is 0, right? So it's not actually because the vector sum of the fields at that particular point is, they cancel out, like the algebraic sum is basically 0 because they cancel out, but simply because it's too far to even get an electrostatic effect on a test charge placed at that particular point due to A or due to B. That's infinity. So the infinity must not be away from, significantly far from the line segment AB. It can, all right, but still along the line segment. So what I mean is go away significantly from B to the left, from A, sorry, or go away significantly from B to the right. So you go significantly away, you get to a point where you put a test charge there, it experiences no force due to any of these charges. So that's infinity. But we can also get infinity anywhere around this region. anywhere around this region, so it must not be along this line segment. So we say that outside the line segment AB, then it means that there's a particular distance outside that we can get to, and then we get the resultant electric field to be 0 at that point. And clearly it's not possible, but if you try to solve it, you would have an algebraic expression for distance. So you just try to solve it like that. The resultant field at any point is EA plus EB. That's the vector sum of the individual electric fields. Electric field is a vector, so you get the vector sum, you simplify, and then you have x. You simplify x is negative half. So if x is negative half, it tells you that this is distance, and we know from physics that it doesn't make any physical sense to have a particular distance as negative, right? So this tells you a possibility of having a solution to this particular quadratic equation, x equals negative half. But in a physical sense, it's not possible for time or distance to be negative. So you must have solved quadratic equations before, where you are getting a projectile, and then you're solving for the parameter t, and then it's a quadratic equation in terms of t, and then you get two values, one is negative, one is positive, and then you, of course, you say it does not make any physical sense to have a scalar to be negative. I think that's exactly the same thing that's happening. Even when you take this m and you take it across to b, you still have the same exact thing happening. You still have a negative displacement or negative distance. Again, it tells you that it's not possible even outside of this line segment to get a distance where the resultant electric field is 0. And it makes a lot of sense from the previous analysis and explanations I've done, right? So our answer here, the best answer is actually E. All right, so our question 2 says the current intensity passes through a circuit for 40 minutes with a capacity of 24,100 coulombs if. All right, so this is not a problem. Our cure, of course, is IT, right? So our I is just cure on T. So I take our cure, which is 24,100 coulombs, divided by our time, 40 minutes, multiplied by 16 seconds. So our I is 10.04 amperes. So our answer is B. Question 3. A 20 ohm resistance motor powered by a voltage of 220 volts and crossed by a current of 10 amperes has a mechanical power of. Mechanical power, take note, mechanical power. So we need to first of all calculate the power that is supplied to the electrical motor, right, to our motor. So we have power supplied is IV, of course. So we have the current that it sucks in, like it draws in, and multiplied by the voltage, the supply voltage. So we have 10 multiplied by 220. So we have our supply power to be 2,200 watts. Now if we go on pH, now what is the pH? Is actually the power that is dissipated as heat, right? Of course, you know that the efficiency of that motor can never be 100%. Why that? Because part of the power supplied is lost as energy per unit time, heat energy per unit time, right? So you notice that the other part is now used as mechanical power, or perhaps energy to do useful work, right? Useful power output. Good. So let's calculate the amount of power that is wasted as heat. So we have I squared R, so we get that, we square it, so we actually have 2,000 watts. So the remaining power would be the mechanical power, right? So the difference between the supply power and the power wasted as heat would give you the mechanical power, which would basically give you the power that is available for useful work. So we have the mechanical power to be power supply minus of course power heat as a result of heat. I've written PW there. All right, so our mechanical power is 2,200 minus of course 2,000, so our mechanical power is 2,000 watts. So our answer is D. The intensity of the electrical force exerted by a charge of negative, all right, that coulomb on another charge that from a distance of 20 meters is given here is that. All right, so of course we are using Coulomb's electrostatic force of attraction or repulsion, but in this particular case it will be attraction. Good. So we have Fk Q1 Q2 over x squared, right? So our k is 9 times 10 to the power 9, so we'll multiply those guys, and then we have an expression 1.125 times 10 to the negative 3. We don't have an answer like that, so our answer is E. So question 6 says 340 meters. Okay, so we can just pause that and read the question. All right. So this is a diagrammatic representation of but this is not really like what is actually the case, because these turns like this are supposed to be very joined to each other. That's why they say joint turns, right? Because our assumption requires that those turns should really be joint turns. Okay, this is gone. So we're now going to say D. I'm going to be using some parameters here. Capital D will be the diameter of the cylindrical core. So this is our core, right? The cylindrical core like that, of course, would be capital D will be its diameter, and our N is the number of turns, right, that we are going to use our copper wire to produce. So our D is the diameter of the copper wire, right? So they've given us the radius of the copper wire as 1 millimeter, so the diameter will be 2 millimeters, obviously. Now you notice that this information of the diameter of the copper wire is not very important to solve this particular problem, right? But there are other things, and I'm going to do the analysis here, that you would require this diameter of the wire to do. Okay, so you know that if we are taking number of turns, if we get a copper wire and we're taking turns along this cylindrical core, what is the length of this copper wire? The length would simply be the circumference of one of these turns, right, multiplied by the number of turns. Okay, that's the length. So you just get the circumference of one turn. If they are quite joined together, right, you multiply by the number of turns, it gives you the length of that wire. So the circumference is what? Is pi d. Multiply by the number of turns, gives you the length. So you simplify that, you notice that our number of turns will be 9999.5 turns. Now I have no idea if you are supposed to round. This is actually 999.4 something something. I've just rounded this already to 1 dp. So I don't know, I don't have any idea whether in the medical school you're supposed to take this answer as 1000 turns. But honestly, if I were to choose an answer, I would pick none of the above. Honestly, I would pick none of the above, because this answer is not precise. That is not what you would have. Well, let's just move on. I don't know. So I think I picked E. I picked E. Honestly, I picked E. I think I spoke with the coordinator of Mufeprek and the coordinator of MIA. I needed to ask them this question: when in a situation like this, what does a candidate do? And I think I had that. I pretty much learned that, well, the candidate has to pick the answer that is written. You know, the medical school is precise. It's crazy. These guys are involved with precision, and you don't have the answer. The answer is none of the above. So this answer is not there, right? So the answer is none of the above. Okay, so we just move on, and we do the other analysis I was talking about. So we can actually calculate the cross-sectional area of. We can calculate the cross-sectional area of the copper wire as pi d squared on 4. When we get that cross-sectional area, of course, we can get the resistance of the copper wire, right? Rho L on A. So our rho, if it's given, right, that's the resistivity of copper wire. L is the length. Of course, we know the length over here, pi d n. Cross-sectional area of the wire, that's it, we've calculated. So we now have the resistance of the copper wire to be 4 rho dn over d squared. So we can now go over and then calculate the field in the magnetic field intensity at the center of the solenoid, right? So at the center of the solenoid, we're actually going to have mu ni, right? But at the ends, it's actually going to be half of this in magnetic field. Of course, you know that. So at these ends, A and B, we're going to have the field intensity will be half of this. At the center will just be this. So I'm calculating the field intensity at the center of the solenoid. So it's mu ni, right? So what is our mu? Okay, of course, it's 4 pi times 10 to the negative 7, right? So we have the magnetic permeability. Permeability of free space. N here is, of course, the number of turns per unit length. So that's why I've gone back to capital N over L, because capital N is our number of turns, L is the length of the wire, and we know the length. And then our current here is, of course, the voltage across the wire divided by the resistance. So we can simplify that. If we knew the EMF that is induced across this wire, right, the induced EMF, we could actually put it in there, and then the resistance of the wire, which we have calculated in terms of the resistivity. So yeah, this is some good work we can do, and I think I've seen this in a couple of Concour questions in the country. So yeah, you could do all of this work and get the field intensity at the center in terms of the induced EMF, in terms of the small d, which is the diameter of the copper wire, and then the capital D, which is the diameter of the cylindrical core, and then of course the other things, permeability of free space. Perfect. So we move on to the next. Okay, when a wire potentiometer is used to compare two electromotive forces, good experimental techniques include. All right, so just pause the question, pause the video, and just read the question. All right. So to get how do we use potentiometer wires to compare EMFs, right? So of course we first of all have a potential gradient multiplied by the particular balance length that the first EMF gives you, right? So we E2 will basically be the potential gradient multiplied by, of course, the balance length you get for that particular guy. And how do you get the balance length? The balance length is simply indicated to you by a very sensitive current measuring instrument, for instance, a galvanometer. So you know that that is L1, which is the balance point, right? And you stop because the galvanometer at that particular point shows zero deflection. So there's no current flowing through it. No, what we are not interested in, let me just say this, because you see option 3 is saying that always checking the constant current through the wire. We are not interested at all in the current that flows through the wire. We don't even care, right? Because comparing the EMFs is not a function of the current that flows through that wire. It's a function of getting this balance length, and getting this balance length is with the help of a very sensitive current measuring instrument, the galvanometer. Oh, I wish I'd drawn the circuit that has the potentiometer wire set up for, or the potentiometer just set up for comparing EMFs. I hope that I'll do that in the next video, because I think in 2019 physics we have a situation of the potentiometer wire too. So I'll just show that illustration in the next video. All right, so we get the balance length with the help of the very sensitive current measuring instrument, and then we have a uniform verification of the uniformity of the wire. So the wire has to be uniform. Why? Because we need a constant potential gradient across that wire. So you don't want to say that, all right, for a particular balance length L1, and then for a particular balance length L2, the potential gradient is different. That would be crazy, right? So we need a constant potential gradient throughout that wire. So it's very important that the wire is uniform, because if the wire is not uniform at other areas where the area is smaller, you know that of course the electrical resistance at that particular point is higher, and of course that destabilize or not unifies, right? The potential gradient across that wire. All right, so that's very important. So the 1 and 2 are quite important. So that's how we compare. So our answer is B here. Okay, the corpuscular character of light is demonstrated experimentally by. All right, so we have all these. Now, all of these options are just options that can be investigated or are demonstrating the wave character of light. So corpuscular means that, all right, if we don't want to look at light as a wave, can we look at it as particles? Of course. Newton actually proposed this and called those particles corpuscles. But the problem is that, well, particularly for refraction, the corpuscular theory could not even explain refraction. Now, the thing with Einstein was, if wave is actually both, or if light is both a wave and a particle, then everything that we have been previously able to explain using the wave model of light, right, like dispersion, diffraction, interference, diffraction, we have been able to explain all these things using the wave model of light. We should be able to explain the same things using the corpuscular aspect of light, right? The particle nature of light, hence the wave particle duality of light. You talk about the dual nature of light, right? Good. So you notice that if we're supposed to investigate the corpuscular character of light, usually what particularly demonstrates that, the experiment that demonstrates that, is the photoelectric effect. And of course the Compton effect too. The Compton effect, you'll see that in college, but the photoelectric effect is what you really see. You do experiments on it, and sometimes the GC board asks you on that, because that's an experiment that demonstrates the corpuscular nature of light. Every other one of these stuff here are basically just stuff that are talking about that can be demonstrated using the wave model of light, right? So the answer here is actually none of the above. So the two answers that would have been ideal for the medical entrance exam would have been the photoelectric effect and the Compton effect. Compton is spelled as Compton, right? Good. So our answer is E. All right, so you can just pause the video and read the question. So we have thorium just basically decaying to a particular dotted nuclide, and then beta with the emission of beta particle. So we can get the proton number of the dotted nuclide to be 91. Of course, it's just the atomic number, and we can also get the neutron number, right? Because this is the proton number, and the mass number is actually the sum of neutron and proton number. So we can get the neutron number to be 234 minus 91, right? So it gives us 143. So our answer is actually E, 143 neutrons and 91 protons. So we have the photoelectric emission is independent of the luminous powers. So is that correct? So let's just check that off. So photoelectric emission is, so for instance, we are incidenting particular radiations here on this our cathode. So this is basically a photosensitive material, right, metal. So it means that if we incident light of a particular suitable frequency, we can experience the emission of electrons from that metal surface. So what are the properties, what are the parameters that would permit that emission to occur? So AC is independent of the luminous power. Of course, it depends on it, right? The incident power, the power of these radiations, whether or not photoelectricity occurs, is a function of that, the power of the incident radiations. So of course we need that. So when you say independent, it means that it does not require the power. So any power, any particular luminous power would release photoelectrons. That's not the case, right? So A is off. B says independent of the frequency of the light radiation. Of course, B is also off. Technically, the amount of energy that's required to knock off these electrons is a measure of the Planck's constant multiplied by the frequency of the incident radiation. That's how much energy the radiation has. So if that energy is sufficient enough, then you notice that they would successfully knock off electrons, liberating them from the electrostatic forces of attraction that keeps them bound to the positive nuclei, releasing them, of course, to move over to the anode if they have enough kinetic energy. So you notice that that is a function of the frequency. So B is again off because it is independent of the frequency. So no. C says independent of the threshold frequency of the metal. No. Why? Because if for instance we are using red light and then photoelectricity does not occur, right, and then we change this material, we'll bring a different material, it's possible that we have photoelectricity occurring for that different material. Why? Because now the incident energy, right, the energy composition of the incident photons must be enough, right, must be at least equal to a particular threshold value, which is basically like the work function of the material, for them to successfully knock off electrons from those electrostatic forces of attraction that keeps them bound. So what we are saying is, if you change this material, you get a different material with a different work function, with a different threshold frequency, it's possible to get photoelectric currents or photoelectric emissions, right? So of course, yes, C is again off because it says independent of the threshold frequency. D says function of the lightning time. Oh, that one is so off. What D is actually talking about is that if I incident these radiations and then photoelectricity does not occur, if we keep it lit, if we keep this particular metal surface lit for like maybe 10 or 15 minutes, after a while when it must have absorbed so much energy, then it's possible that photoelectricity occur. Of course, that would have made sense if the wave model of light could explain photoelectricity. It would have made sense. But because photoelectricity is explained by the particle nature of light, so you're basically looking at the transfer of momentum, the momentum of the energy possessed by the individual photons. They're transferring that momentum to, of course, the electrons, and they're getting knocked off, so that is what explains the photoelectric effect of light. And so it doesn't really make sense to think of it like the lightning time. So photoelectricity, in a nutshell, is an instantaneous process, right? So if it's supposed to occur immediately, you're eliminating the light, the metal surface, the photosensitive metal surface, boom, it occurs. So the answer right here is actually E, because none of these guys are actually correct, right? So, but we can do the analysis here, right? The energy of the incident radiations minus the work function of the material to be equal to the kinetic energy of the photoelectrons, because when you knock off, it depends. You can actually move or not move, right? So if this incident energy is directly equal to the work function of the material, photoelectric emissions occur, but the electrons don't have enough kinetic energy to move across the anode, right? So good. So you need to increase the energy of the incident radiation to give them enough kinetic energy so they can move across. All right, so we can do that. Kinetic energy is half mv squared. We can actually do in a particular case where we are stopping these electrons. So when they move over to the collector plate and they are eventually stopped such that no photoelectric current flows here, because when these electrons move over from the cathode to the anode, right, so the electrons flow through this circuit. So this ammeter records a small current, right? It's called a photoelectric current. So but we will apply a particular voltage across this anode such that when the electrons move over from the cathode and they are eventually just stopped at the anode and they don't flow through the circuit, then we call that the stopping potential, right? So we can actually say that the entire kinetic energy of the electrons is actually used up to stop them at the anode, right? So that's why we're saying that EVS is equal to this kinetic energy, right? Good. So work done in totally stopping the electrons. So we actually know that our answer here is just E. So we can move on to the. So we have, for a given photocell, which of the following proposals are correct? All right. So A says the output electrical current depends on the wavelength of radiation used. Not true. Now, okay. So this is our output electrical current here. This is a photoelectric cell, right? So incident radiations, they hit the photosensitive metal surface. If they overcome the surface potential, then electrons are ejected, and then the electrons are collected by the anode, which is called a collector, and then of course the flow down the path, and then of course photoelectricity is generated, photoelectric current flows. Now my worry here is, if we have incident radiations and we increase the energy of these radiations. So if we increase the energy of these radiations, what we're basically doing is we are not increasing the number of electrons that are ejected from this cathode. We are not increasing the number of electrons. We are simply increasing the energy of the kinetic energy of the electrons as they are ejected when you increase the energy here. So when you change the wavelength, or you change the frequency, or any component that directly affects the energy of the incident radiation, then you are affecting the kinetic energy of the photoelectrons when they are ejected. Okay, so by so doing, you would be affecting the stopping potential, because if you increase the kinetic energy by increasing the energy of the incident radiation, probably by increasing the frequency of the incident radiation or lowering the wavelength of the incident radiation, then you have to increase the value of the stopping potential. Also increases, because the kinetic energy of the photoelectrons now is increased. All right, so what happens if you want to get an increased photoelectric current? If you want to get an increased photoelectric current, what you have to do is increase the intensity of the incident radiation, not the energy, the intensity. So the intensity now is the energy per unit time, which is basically like the number of photons that are interacting with this metal surface per unit time. That's how you can think about that. So if you are increasing the number of photons that are interacting with this metal surface per unit time, you notice that you will be knocking off more electrons per unit time, and more electrons are collected by this anode per unit time, and more electrons flow to this circuit per unit time. So that's how you get to increase the photoelectric current, right? So A is off, right? So B says the threshold frequency does not depend on the metal of the cathode, but on the metal of the anode. That's not even true now. Threshold frequency is based on this guy, because this is where the photoelectricity occurs. Thank God I've not drawn it here for you to see. So the cathode is what cathode is a photoelectric metal surface. Okay, so it's the guy that ejects the electrons. It's like the emitter. Good. So we have the cathode there. So B is off, right? Because it does not depend on the metal of the cathode. So that's wrong. So C says the threshold frequency depends on the number of photons arriving per second on the cathode. Of course, that's not true, right? That's like a function of the intensity of the incident radiation, not the threshold frequency. Threshold frequency is an intrinsic property of the material. It varies from one metal to another, not about the radiations themselves. All right, so D says the intensity of the current output is greater when the cell is turned on with visible light than with ultraviolet light. Is that true? All right, so that is not even true. Listen, the very first thing is that we're talking about the intensity of the current output. Is it really greater? Does it change when you change the light, or a particular photon of maybe ultraviolet, or a particular photon of visible light? It does not. Now look at this. Even if it had to change, right? Because what really changes when you change these things is the energy of the photoelectrons, right? Because if you change the radiation that is used from visible light to ultraviolet, then you are saying that a photon from the ultraviolet spectrum, come here, this is electromagnetic spectrum. So a photon from this ultraviolet spectrum, region of the electromagnetic spectrum, would have more energy because it has a higher frequency. So as the lower you come, the higher the frequency. The further you go, the smaller the frequency and the bigger the wavelength, right? So and a photon of ultraviolet would have a higher frequency and hence a higher energy, and hence the photoelectrons that are ejected would have a higher kinetic energy, and that's all. It has nothing to do with the intensity of the current output. What the intensity of the current output affects is the intensity of the radiations. So if we increase the intensity of radiations, right, we are increasing the number of photons that are interacting with our metal surface per unit time, and of course all of that. Good. So D is off. So our only answer here is again E, none of the above. So our answer is E. Perfect. Okay, again, you just pause the question and read. So we actually have so there are very two important equations that I use, in solving radioactive problems. So we actually have a n0 over n final equals 2 to the power n. So the initial activity, or the initial number of atoms that are present in the particular radioactive sample, divided by the final number of atoms that are present, or the final activity, right, is 2 to the n. So in this case, we are getting initial activity and final activity. We get that ratio. So we get n, we just basically find n. So we take ln on both sides. So we actually have n to be ln that on ln 2. So our n is 0.255. So T equals to NT half. So these are like the two most important equations for the activity that I use. N0 over N equals to 2 to the power N, and T equals to NT half. So when you get N here, you now put it in here. The half-life of the radioactive sample is actually 8.04 days. So we actually have T to be 2.05 days, and our answer is A. The threshold frequency of a photocell is a function so the intensity of the photoelectric current, wrong. The intensity is a function of course, the intensity of the incident radiations, which is basically like the number of photons that are interacting with the metal surface per unit time. So BC is the wavelength of light radiation. The wavelength of light radiation is a function of the kinetic energy of the photoelectric current, or the photoelectric the photoelectrons, damn it. All right, so C says target metal. So yes, because the threshold frequency varies from one metal to the other, right? So it's basically like a measure of the surface potential energy that the material has. So how much surface potential we need to overcome in order to get photoelectric current or photoelectric emissions. So that's a measure of the surface potential of the material. So it varies from one metal to another. So C is actually the right answer. But let's just go on to this. Is the electrons mass. Of course, screw that. If electrons had variable masses, then this would have been true. If like the mass of electron in zinc is different from the mass of electron maybe in let's say lead, right? And both of these guys are photosensitive surfaces, then of course photoelectric emission would depend on the mass of the electrons, right? Because then you will not be overcoming just the electrostatic force of attraction, but you're also overcoming the huge inertia, right? Because objects at rest want to stay at rest, so they are orbiting a circular path, they want to stay in that path, but you want to cause them to move in a certain direction. So you have to overcome a very huge inertia, and the bigger the mass of the electrons, the bigger the inertia you have to overcome. So in that particular case, that would make sense, but the mass of electrons does not vary, so this makes no sense. Screw none of the above. All right, so our answer is actually C, target metal. Good. Okay, I'm just going to talk about this, and the answer is actually B, right? The origin of Laplace strength is electromagnetic. Now, the problem here is that when you study magnetic fields in high school, and of course electromagnetic induction, where you're getting to study a charged particle, for instance, moving through an electric and a magnetic field, right? So we can the resultant force that acts on that particular particle is known as Lorentz force, right? And it's a sum of the electrostatic force, the electric force that's exerted on the charged particle and by the electric field, and of course the magnetic force that is exerted on the charged particle by the magnetic field. So you are getting to sum two forces. Basically, the electric force is basically just the electric field strength multiplied by the charge on the charged particle that's moving through that field, plus the magnetic force now would be of course B Q of V, where B is the magnetic field intensity, Q is the charge on the particle, and V is the velocity of the particle, right? So when you sum these two forces, you get Lorentz force. Now, Laplace's force is now talking about us not moving a charge through this field. We are moving a wire, for instance, right? A current carrying wire. So, and then it's being moved through a magnetic field, okay? So, and then we're still studying the effect of electric and magnetic field working together, which is basically electromagnetic then, but then not for a charged particle, but for a wire, for instance. So that talks about, we're not talking about Laplace's force, all right? So they are quite similar, and we see that in electromagnetic induction. All right, let's move on to the next. So the distance between the Earth and the Moon is that, and the ratio of the masses of the two planets is that. The equigravity on the axis, the equigravity point on the axis between the two planets is. Okay, so we can, at a point where, of course, we have equigravity, it means that at a point where if we put a point mass at that particular point, the resulting force on that particular point mass is 0 at that point, right? So the Earth is pulling on it equally as the Moon, right? And they are opposite directions, so the two forces are opposite but equal in magnitude. So boom, net force on the particle is 0. So GE must be equal to GM. So we actually get the relationship for GE is GMT, because MT, according to the question, is the mass of the Earth, so R minus X. So X now is the distance from that point to the Moon. That's why I'm just having X squared here, GM1 over X squared. All right, so we simplify, we actually have R minus X equals that, so we simplify, and we have X to be equals to this, because R of course is the distance between the Earth and the Moon. That's the total distance between the two heavenly bodies. So we now have X to be equals to that, of course. So because X is the distance from the Moon, so directly is from the Moon. Make sure that your answer is, this answer here will be in meters. So when you convert it to kilometers, you'd basically be taking off I think 3 significant figures from the left, from the right actually, right? So it gives you this answer. Okay, so our answer is C. Thank you guys so much for watching. We have actually come to the end of our YouTube video, and we hope that you liked it, and we hope that you can stay around and help us reach more people, share our video, share our content. So like over here is what we want to use YouTube for, and you can just pause that debate and read. So if you want to contact us, you want to reach out to us, maybe you want to recommend what videos we should solve next, just that's my contact. It's on WhatsApp. You can WhatsApp me, and then we talk, and then you leave them. You want us to solve engineering past questions, you want us to solve anything, so reach out and contact us. If you want to join the team, because we have a huge passion for the community, and if you want to join us at Knowledge Center, reach out. Thank you so much for watching. Stay fine and stay curious always.